Okay, so today we are going to address the logistic model in detail without solving the differential equation. We are going to take a qualitative approach to analyzing the model without solving it, even though it is solvable. So it all begins with a very basic linear ODE. A rate of change of a population is proportional to the population. That is generally true when the population is small. As the expression goes, trees don't grow forever. If you look at an exponential growth model, it never grows exponentially forever, because there are other social constructs that prevents it from moving in this direction. It might start up to here, let's say. It might start the same way. I'm going to change the color. And then it takes a path of its own. And generally, not always, but generally, things stabilize. So we cannot extrapolate just because you have an exponential model. As you know, if you use the separation of variables on this model here, on this ODE, you will get something like P of t equals some sort of an exponential growth with an initial population P0. Okay, just separate the variables. I'm sure you can all do this. So what we want to do really is to figure out how to model this red curve, which is more realistic. Okay, so let's just consider that there is a carrying capacity n. Let's call this a carrying capacity n. This is where the population stabilizes, and if the population is greater than the carrying capacity, that means the population would have to decrease. And if the population decreases, then the rate of change has to be less than zero from calculus, right? If f is decreasing, then f prime is negative. That's what I'm trying to say, okay? And you could continue on this and say if the population is the carrying capacity, then it just stabilizes there, and of course there is no rate of change. And if the population is less than the carrying capacity, then you expect the population to increase to reach that carrying capacity, and therefore the derivative, or dp dt, is more than zero. Now, how do we put all of these together, this one, and this one together? I'm going to go back to the first one, this one, and they're here. So if p is more than n, right? If p is more than n, then clearly p over n is more than 1. And if I multiply both sides by -1 and add 1, I get 1 minus p over n less than 0. Which also means that the rate of change is less than 0. I could do the same thing for the second piece here. So if p equals n, then p over n equals 1. And if you multiply both sides by -1 and add 1, you get this quantity. And therefore dp dt equals 0. And the last one, if p is less than n, then p over n is less than 1, and you do the same thing and you get this. The reason I'm saying this is because this differential equation doesn't take into account that dp dt can be negative or positive. We know dp dt is positive because the population is positive, and generally this constants, coefficients, the rate of change is positive. We want to take this red curve into account, and therefore what we want to do is try to put all of these three pieces together in a picture. And the model looks like this. And I'm going to show you this model in a very different way. dp dt equals kp, dp dt equals kp. I'm going to insert a quantity that is either positive, negative, or 0. And we call it 1 minus p over n, as you saw in here. Okay? So, the model now, I can't get rid of this. There you go. The model we're going to use instead of this one is going to be this one. Okay? Now, this is a logistic model. It is a nonlinear differential equation, as mentioned before. It happens to be solvable, and I hope you took a stab at it. It's really just use separation of variables, use a little bit of simple fractions, not simple fractions, but partial fractions. I'm thinking of simple fractions is another concept from number theory. Partial fractions, and you should get a solution, but you don't have to. What I would like you to do is to consider this function as a function of p, right? And it looks quadratic, isn't it? Because it looks quadratic, we can graph it. Now, I can rewrite it this way so you could see. So dp dt equals kp minus 1 over n p squared, minus k over n p squared. It's quadratic. The leading coefficient is negative, so it has to be facing down. And the factors, what makes dp dt 0 is either p equals 0 or p over n equals 1. P over n equals 1. This quantity is 0. That means p must be n. So I put in here 0 and n, and I drew this quadratic curve, and I deliberately went below the x-axis to make a point. I understand that the population cannot be negative, but I'm going to try to make a point. So now, look at this. We can actually do everything we want to do just through this graph. This graph is called, as you will see, is called a phase plane. Okay? It's called a phase plane. Let me erase this. All right. So watch this. If the population is between 0 and n, clearly dp dt is more than 0. And if dp dt is more than 0, because it's above the x-axis, right? dp dt is more than 0 when p is between 0 and n. That means the population has to increase. So anywhere where p is here, the population has to increase. So that's why I put the arrows to the right. If p of t equals 0, that means dp dt is, if p of t equals 0 or n, that means dp dt equals 0. That's obvious. However, if p of t is more than n, let's say you're here, okay, at that point, dp dt is negative. It's below the x-axis. It's here. And therefore, the population has to decrease. Similarly, if the population is less than 0, if the population is here, dp dt is negative, and therefore the population has to, decrease. So what we discover here is this point, p equals 0, and p equals n, are called points of equilibrium. Points of equilibrium. However, if you pay attention to the arrows, when P equals N, which is a point of equilibrium, the arrows seem to head toward one another. That is called a stable point. And if P equals 0, which is a point of equilibrium, the arrows seem to move away from 0. That is called P equals 0 is not a stable point of equilibrium. So even though both are points of equilibrium, one of them is stable and the other one is unstable. And you could see it through this curve. I'm going to do P of t against t. Not dp dt against p, but P of t against p. Okay? So, we have two points of equilibrium. One is called P equals 0 and P equals N. If P is between 0 and N, look back at the graph. If P is here, then dp dt is positive and therefore the function has to be increasing. So anywhere in here, your function P of t has to be increasing. So let's say the population is P0, okay? It's going to have to increase. But then N is a point of equilibrium, and so as 0. So the population would have to stabilize around N, okay? If P of t is more than N, let's say it's here, then we know, based on the first graph, the population has to decrease. Why? Because dp dt is less than 0. So if you are here, the population has to decrease. If you are at 0, or actually below 0, it's silly. But let's say the population is less than 0. Go back here. We say dp dt is negative, and therefore the population has to decrease. So if a population is here, it'll just go downhill. And if it is more than 0, it will definitely increase again, right? And it's going to stabilize. So do you see that when P equals 0, that's a point of equilibrium. When P equals N, that is also a point of equilibrium. P equals 0 is unstable because a small change from 0 creates chaos. One goes in this direction and one goes in the other direction. However, if you move away from N, let's say here or here, it is a stable point because the population comes back to the point of equilibrium. And that's the point I want to hit home, which is not mentioned in the book. So I'm going to draw a little picture for you so you understand visually what that means. So let's say I have two bowls. Okay, sorry. Two bowls. And I have, let's say, an apple. I put an apple here. Oh, my God. I have an apple here, and I have an apple here. Okay? So this apple is in equilibrium. You could literally let it sit on the top of the bowl. And this apple, oh, I hate this apple. Let me erase it. Okay, so let me start over. Oh, my God. I can't draw. Small perturbation of this apple will create chaos. It's unstable. Unstable. But if you move this apple a little bit to here or to here, it'll come back to its position. This scenario is this scenario. And this scenario here is this scenario. So both of them are in equilibrium, hopefully. Both apples are sitting at this one is sitting at the bottom and this one is sitting at the edge. They are both in equilibrium, but one of them is stable and the other one is unstable. Okay? So this is extremely important. This concept is very important. I'm going to end very quickly with, I mentioned this in class the other day, and I said this is a nonlinear logistic model. And today we kind of came up with this one, and they're basically the same. I'm gonna illustrate this with an example. Let's say you have, you have a population of fish. Okay, so you have a population of fish. And it's a large population, let's say. Okay. Let's say you have of size n. So let's say you have n fish in some, body of water. Every fish has the ability to encounter n minus 1 fish. Sorry, n minus 1 fish. Every fish can encounter n minus 1 fish. And therefore, if you have the population P can encounter P minus 1. Right? Can encounter P minus 1. And if you multiply these together, you get P squared minus P. Now, if the population size is large, remember, we only use this when the population size is very small. But most populations are very large, and for this reason, this is not very practical. We don't necessarily use this. We have to resort to these. If the population is large enough, if P is large, then we can ignore P in front of P squared. So basically, you have a growth rate called A. In the book, it calls it K. It doesn't matter. Okay? So a rates of change of a population is proportional to the population. But then we have to take away, this is called death rate, because fish eats fish and fish dies and resources are scarce. So you've got to subtract something. So this K or A is the growth rate. And S is the death rate. And so you have to subtract a multiple of this. But we're going to ignore P because of this, because P is large. And that's why we take away a multiple of P squared. So this model is exactly this model. Of course, you know what S is. S is K over N, isn't it? So if you multiply this together, you get K minus K over N P squared, Kp minus K over N P squared. This is A, and K over N is your S. And that is, so the carrying capacity is K over S. right? Or A over S in our case. That's your carrying capacity. So I could repeat everything I did earlier and do this. This is 0, and this is A over S, which used to be called N, and this is halfway through, and you can play the same game. Okay, so this is dp dt, and this is P or P of t. Okay, so so to make the points that these are exactly the same, we kind of found a way to create this one, and I showed you how you can pull this one using this example of fish, and they're basically the same. So this is called the logistic model, and I am going to end the video right now.